Right, so I'd just like to welcome you to the last but one, if we ignore the prize giving, part of our Carbonate Forum meeting. We have a discussion which involves contributions from Rachel Wood, Nick Tosca, and Sasha Turchyn. And as yesterday, we hope that this will kick off lots of discussion within this session and potentially extending a bit later. I'm going to pass straight over to you, Rachel.
Well, welcome everyone to this final forum discussion. We've chosen a really hot topic where there is not yet any really firm emerging consensus. Maybe there is in some areas, but not in all. And this is a topic that's been really explored to date, mostly by our geochemical colleagues. And so for this reason, I've invited two distinguished geochemists who both have worked on this topic, Nick Tosca and Sasha Turchyn from the University of Cambridge. We're going to follow the same format as yesterday with, we're all going to say a few words, but predominantly first Nick, then Sasha, and then I'll just sort of tie things up a little bit at the end. We will have, during our presentations, we will raise some questions for discussion and we'll put these up at the end. And what I propose is that we follow that framework of those posed questions for the remainder of our slightly more free-flowing discussion. We'll try not to use hands. We'll try to have this a free-flowing discussion. Obviously, please feel free to use the chat, but don't bother about putting your hands up, just wade in. And also just a reminder, please, no recording. Thank you very much. So I'm going to hand over to Nick now.
Okay, thanks, Rachel, and thank you for inviting me to lead this part of the discussion. I'm going to share my screen here, and hopefully you can all see this. Yeah, so I'm actually just going to say a few words about dolomite to the extent that dolomite forms a principal component of the sediments from which many chemostratigraphic records are based. We thought it was important to at least include dolomite in the discussion. As you'll see in just a couple of slides, we'll kind of pose some, deliberately provocative discussions that should hopefully promote some discussion. So I'll just provide a brief introduction to the question surrounding dolomite and its potential significance in the global carbon cycle. We're all very familiar with what's been labeled the dolomite problem, which is basically that we don't really understand the environments in which most marine syn-depositional and early diagenetic dolomite formed. And there are many examples of which that can be found where dolomite dominates the carbonate sedimentary record. But a notable example is through much of the Precambrian, where it's long been documented over the last several decades that the abundance of dolomite and many marine carbonate successions changes as you move through the Precambrian and into the Phanerozoic. And we understand, and observations have noted this for the last several decades, in fact, stretching even further back in potentially 100 years or so, that the style of dolomitization is also very different, moving from the Proterozoic to the Phanerozoic, in that syn-depositional and early diagenetic dolomite in marine carbonates seems to have been more common in Proterozoic seas. And it also seems to have been common in specific intervals within the Phanerozoic record itself. And I just include just a recent compilation from a publication by Canteen et al. 2020 that kind of provides some more recent data to document this trend. See, right. So in the last several years, we've also started to better understand what's been labeled syn-depositional or as close to primary dolomite as we might be able to get, in the form of these examples here that Ashley Hood and colleagues have documented over the last few years, radial fibrous dolomite cements in cryogenian reef complexes. And there have been many other examples of this type of fabric. And the significance is that this suggests that ambient seawater at this time was itself, in fact, dolomitizing fluid. So there was something about seawater, about the conditions of deposition and diagenesis that lended itself to the crystallization of dolomite directly from that seawater in cavity filling fabrics. And this evidence has kind of sharpened the problem, and that it's very clear that seawater was capable of doing this, and yet we don't really understand the chemical or environmental conditions through which this is possible, certainly in comparison to modern seawater. Now, obviously, as we all know, there's been no shortage of suggestions, and many of these suggestions center around finding what I've sort of labeled, in a deliberately provocative way, that the magic ingredient which might be required to crystallize dolomite from seawater. One of the first that generated a lot of discussion was sulfate. Initially, it was thought that sulfate might inhibit dolomite precipitation, but obviously there's been a lot of conflicting results surrounding sulfate, and more recent examples include a special role for manganese associated with anaerobic photosynthetic metabolisms. One of the, I guess, unsatisfying aspects of some hypotheses surrounding the quote unquote magic ingredients for dolomite and seawater is that they don't universally apply to modern environments where we know dolomite forms, or in fact order dolomite. So for example, in caves and other freshwater settings, or in paramarine settings. And so that's always kind of stood out as not a very satisfying aspect of several of these hypotheses. And yet, we need to understand the role of various or at least be able to rule some of these out. So I guess the last thing I'll say here is that potentially the recipe is the problem, or at least we've been thinking about that the recipe to form dolomite in the traditional way, just like we do with most other minerals, in that the mineral must crystallize ion by ion from a solution, and that it's the ingredients that are the problem. But another possibility is that it's the recipe that's the problem. And I show an example here of a kinetic study by Arvidsson and McKenzie, where they determined the growth rates of dolomite as a function of temperature in different solutions. And the conclusion was that the rates of dolomite crystallization from water are just too slow to explain many fabrics that we know and love from the carbonate record. And so this really creates a problem, and that maybe we're thinking about the recipe in the wrong way. Maybe you can form dolomite in different ways aside from just the ion by ion classical crystallization pathway that many geochemists are used to. And so obviously in the last couple of years, there have been some studies suggesting that precursors could be important. So this is a thermodynamic study of the relative energetics required for forming amorphous carbonate phases in comparison to their crystalline counterparts, calcite, magnesite, and dolomite. And those data suggest that energetically it's possible, in fact, in some environments even favored, that you could potentially get to dolomite through a precursor. This is a potential advance in our understanding, but of course it leads to the question of, well, what's the significance and the exact role of the precursor as such. And so that issue still remains quite foggy. But I think there's progress to be made in understanding the recipe for dolomite formation and the extent to which it informs environmental conditions under which it could have formed through much of the carbonate record. So I'll just kind of leave here a couple of deliberately provocative discussions questions that I hope we can base our discussion around a little bit later. The first is that we've known for a long time that key geochemical parameters certainly play a role in dolomite formation. Things like enhanced alkalinity tend to favor high dolomite precipitation rates. We think relatively high magnesium-calcium ratio. There's kinetic and thermodynamic basis on which to rest that conclusion. How much does knowing the other environmental conditions of dolomite formation really matter in the context of its significance in the global carbon cycle? I guess another question that at least I've been thinking about is that, well, if a magic ingredient was needed in seawater, why don't modern dolomite formation, or why don't modern dolomite forming environments conform to those requirements? You know, is it the ingredient, or is it actually the recipe and not so much the ingredient that's the problem in forming dolomite? And lastly, and I think the third question that really ties into what Sasha is going to talk about and what Rachel will talk about, and probably where much of our discussion will lead, is that given that dolomite forms such a large component of the carbonate record from which we derive our chemostratigraphy, what role did dolomite play in the global carbon cycle? You know, to what extent did diagenesis, or does diagenesis alter the capacity of dolomite to record aspects of the waters it forms? And then conversely, you know, if dolomite was such an important precipitate in syn depositional and early diagenetic environments, what impact did it have in the carbon cycle? Does it matter that that there's actually a difference in alkalinity and DIC per mole of dolomite formation relative to calcite and aragonite? What's the biogeochemical significance of that reaction, or any other components that are actually required to form dolomite itself? So I'll kind of leave that there and hand over to Sasha and kind of leave those questions and other issues stewing in your mind. Right, so let me just stop sharing. And yeah.
Okay, thank you. And yeah, and thank you as well for being invited to come and talk today. And I need to offer a small apology in advance that I'm actually in my office, my physical office, and the Wi-Fi here is terrible and it's been dropping out on me all day. So I apologize if I freeze sort of mid-sentence. So when we think about the sort of topic of the debate here, the discussion, the role of carbonates over Earth history, I immediately thought about the role that carbonates play in carrying all of our paleoceanographic and paleoenvironmental information. And I wanted to introduce, again, similar to Nick, just a few slides to talk about this standard assumption that the carbon isotopic composition of carbonate minerals and rocks tells us about how much organic carbon has been buried over the course of Earth history. And I want to introduce this, and then I'm going to also put up a few sort of provocative points for us to sort of discuss later on as to whether or not we think that that's actually valid. So first, for those who don't think on these sorts of timescales or about carbon isotopes at all, where does this come from? Well, if we think about the geological carbon cycle, we often approximate it as sort of a single box where we have an input, and this input comes from volcanoes, rocks, weathering, metamorphism, anything that releases carbon to the surface of the planet from the lithosphere. And carbon is removed in the form of either carbonate minerals or in the form of organic material. And effectively, if we assume that the isotopic composition of all the carbon that's coming into the system has to equal the weighted average of all the carbon that's going out of the system, then we can come up with sort of a very simple mass balance. So the way that this equation works is that the isotopic composition in terms of its carbon isotope ratio of what comes in, so that is the sort of sum of the volcanoes and the rocks and anything that's releasing carbon to the surface, is going to be equal to the fraction that leaves as carbonate minerals times its isotope ratio, and then the fraction that leaves as organic carbon times its isotope ratio. And if we assume very nicely that there's a sort of globally average fixed carbon isotope fractionation between the inorganic carbon and the organic carbon, this allows us nicely to sort of solve this equation. Right? That is to say that if we make an assumption about what the isotopic composition is that comes in, that's all of these red arrows, and we make an assumption that the global carbon isotope fractionation from carbonate minerals is 27 per mil, you know, and then we go to our nice mass spectrometers and measure the delta C13 or the carbon isotope ratio of carbonate minerals in the geological record, we can then solve for what we think is this really critical parameter, which is the amount of organic carbon that's buried over time as a fraction of the total carbon output. And what I'd like to do is throw up a few wrenches, I think, in this standard view of how you interpret carbon isotopes and carbonate minerals. So the first one is this assumption here that we know what the carbon isotopic composition is of what's coming into the system. This is typically assumed to be -6 or -5, depending on your favorite number for the mantle, like global average mantle delta C13 of DIC. And there was a paper, we had a paper that came out a couple years ago that actually looked at the carbon isotopic composition of lots and lots and lots of different volcanoes and did weighted average fluxes and showed that today it's not -3, at least from volcanoes. It's closer to, sorry, it's not -6, it's closer to -3. And indeed, we think it's probably buffered very close to the values associated with carbonate weathering, because that's going to dominate the carbon that's released from a rock into Earth's surface environment. So the question would be whether or not this isotopic composition of what's going in can be assumed to be more or less constant over Earth history, or whether it might vary as a function of, pick your favorite, supercontinent cycles, or, types of volcanism, arc versus continental volcanism, or types of mid-ocean ridges. Exactly what would that isotope ratio be that would effectively set this equation? The second question would be whether we can always assume that we have a global average isotope fractionation from inorganic carbon. And I would argue that there's enough play within, the isotopic composition of organic material that might not always be the case. And that in different preservational environments, so different places where you're actually making sedimentary rocks and putting organic carbon into mud, into rock eventually, and removing that carbon atom from the surface of the planet, that actually you could preferentially be preserving something that is not quite 27 per mil. In certain places, maybe you're preserving something that's much, much heavier. In certain places, maybe you're preserving something that's much, much lighter. And I don't know that that's the case, but it seems to me with the fact that organic carbon itself, any given molecule can range over 20, 30, 40 per mil, suggests that assuming that we're always at the Rubisco fixed fractionation might not be a fair assumption, and that in and of itself might also vary. So I'd like to sort of put out there that different types of organic carbon can be preserved in different environments, and we know that preservational environments evolve over time, and therefore, making this sort of standard assumption might not be true. And the final question would be effectively, what about this carbon isotopic composition of carbonate itself, right? Is that representing the global delta C13 of all inorganic carbon at the surface? And I'd argue no, probably for several reasons. This is sort of one of my favorite papers that shows this, but there's lots of papers that have shown the nature of how the carbon isotopic composition of different minerals can change during early diagenesis. And that the nature of that diagenesis, if it's sort of neomorphic versus a whole scale recrystallization, can affect the carbon isotopic composition of what's ultimately removed out of the bottom of a sediment pile, and therefore the relative amount of 13 and 12 isotopes that you have to play with. Oops, sorry. Yeah. So we know that the carbon isotope fractionation of different types of polymorphs of calcium carbonate can be preserved differently as a nature of recrystallization. And so considering that when we're thinking about a stratigraphic section and assuming that my carbon isotope ratio of my particular carbonate rock represents the global carbon cycle is something that needs to be considered within the context of what we know to be that variability in the modern ocean today. So this was the standard assumption, right? The carbon isotopic composition of carbonate minerals tells us about this fractional organic carbon burial over Earth history. And again, these are provocative questions, but here are the questions I would put, effectively put for us to sort of consider. That variations in the carbon isotopic composition of carbonate minerals should be interpreted outside of variations in fractional organic carbon burial, or that you must justify why the variation is only that of fractional organic carbon burial. And that's excluding things like perturbations where you might have release of carbon to the surface and a recovery or a time period, that kind of thing. And that the carbon isotopic composition of carbonate minerals rocks reflects in part local rather than global processes and should be interpreted as such. That variations in any given stratigraphic section are as likely as likely, not definitely, to reflect changes in depositional environment as they are to reflect changes in the global carbon cycle. And then the final provocative question would be whether there's any utility in just measuring the carbon isotopic composition of an old carbonate rock and interpreting its variation outside of a diagenetic context. So those are my sort of thoughts about the role of carbonate minerals over Earth history. And I think I'll hand over to Rachel.
Thank you, Sasha. So what's being presented is really in terms of the importance of local over global is very, very persuasive, and that these dynamics have really changed through time. However, if we just take the long-term consequences of what would be the long-term consequences of these new insights. So first of all, this is a recent paper, not the same compilation that Nick mentioned, but another compilation, just looking at sort of normalized dolomite abundance through the Phanerozoic. And the suggestion here is that there's a close correlation of dolomite with mass extinctions. And the key mechanism that would connect those would be the rise of anoxia. So it's been suggested by many as anoxia being yet another one of these possible variables that promotes the formation of dolomite. But the actual mechanism is utterly unknown, really, in any detail. But you can see here this correlation of the dolomite abundance with these 5 major mass extinctions. Now, of course, if you believe that, it tells us that there is something environmentally important that the dolomite distribution, or at least abundance, is telling us. Now, carrying on from what Sasha said in terms of carbon isotope excursions, perhaps telling us more about the local conditions, rather local depositional and diagenetic conditions, particularly issues of onshore, offshore, burial of different types of carbonates, and also different types of diagenesis, so whether we're dealing with fluid buffered or sediment buffered diagenesis. And if we consider then this so-called global composite curve of carbon isotopes through time, which we see reproduced very, very frequently, how much of this is really reflecting of a global carbon cycle? Now, we all know that seeing a curve like this is far from accurate. It's really a cloud of points where you can put an average through the cloud, and there's enormous variability in a lot of these excursions. However, having said that, there is no doubt that some of the biggest excursions of the Phanerozoic, for example, the N-Permian, a whopping negative excursion, quite complex, it's found almost everywhere, and it really coincides with a mass extinction. So, for example, here, just a study that I was involved with, looking here at the Permo-Triassic, here's the excursion. In fact, this instability of the carbon cycle continues for quite some years into the early Triassic and then the mid-Triassic, when it finally becomes sort of normal, inverted commas. This corresponds to very, very dynamic redox, the coming and going of an oxygen minimum zone that's inflating and deflating. And this does correlate with periods of OX6 habitable space coming and going. So if these carbon isotope excursions can best be explained by local diagenetic phenomena or depositional and diagenetic phenomena alone, why on earth would they correspond to patently dramatic changes in our history of life? In other words, massive biological turnovers or mass extinctions. Now, of course, what really ties all this together would be to find mechanisms that can tie together potentially key parts of diagenetic change with carbon cycle change and biological turnover. That's what we might seek to integrate to try and understand this. So these would be my 2 pennyworth questions for discussion. If these carbon isotope excursions, if these mechanisms are depositional diagenetic, do we not then need to find global mechanisms? There's no doubt that local diagenesis is supremely important to understand. We all know that as carbonate petrographers. But what is the linkage? Is there a linkage with diagenetic style? So for example, sea level change. We know it's been long understood that a lot of extinctions correspond to quite significant regressions, and the Permo-Triassic is certainly one. And so surely there is a key role here for us as carbonate petrographers. It is a very rare geochemistry paper that has any carbonate petrology in it at all. And I think that's something that really, these two worlds really do need to come together and be integrated. So I've just put together the questions that were raised by all three of us here, Nick, Sasha, and myself. We're all, chasing aspects of the same issue. And what I suggest is that we start the discussion. I'm not sure I can keep this up actually. If I'm sharing my screen, maybe, yeah, I'll keep it up and initially, but please do now fire some questions at us.
Just to let everybody know, I'm opening the chat so people people can ask questions via chat, and you can also ask questions by turning your mic on.
We could get this going slightly by having a little bit of a provocative debate amongst ourselves until somebody pops up with a question. Unfortunately, I actually can't see the chat if I'm sharing my screen. This is a tricky technical issue.
I can keep an eye on the chat for you, Rachel.
Excellent, thanks, Fiona. So we have a problem here between if these carbon isotope excursions are dominantly local, how can we explain the fact that they are corresponding, not all of them, of course, but some of them are definitely corresponding to really significant mass extinction. So Sasha, how might, since you've posed that, how might you explain that?
Well, I think I said that, in theory, in theory, a carbon isotope excursion or a carbon isotope perturbation, might exist separately from our understanding, things about like the Permo-Triassic boundary. But if you look at Clino in the Bahama Banks, there's a 4 per mil excursion in Clino over the last, Peter could chime in and tell us how long it's taken to deposit that, right? If that were preserved today, you would be seeing a 4 per mil excursion in the carbon isotopic composition that has nothing to do with anything else. However, that's a purely mineralogical signal that's being preserved, and diagenetic signal. However, you might flip it around and say you might preserve a carbon isotope excursion that is in part some perturbation to the carbon cycle, and it is part a change in depositional environment that's associated with that change in the carbon cycle. Like, for example, a sea level change or some other change in the depositional environment that affects the carbon isotopic composition of carbonate minerals that are deposited at that point in time in that particular place. So in some way, it's whether, whether the composite figures that make the very nice curves for the carbon isotopic composition over the Phanerozoic actually need to be considered in terms of not just of their geochemistry and a 5-point running average, but more in terms of the individual depositional environments and how they've evolved and how that might affect the preserved isotopic composition.
I think that's absolutely true, but I know that there are multiple papers in the literature now that are, so one example is the end Ordovician extinction, the Hernantian carbon isotope exclusion, which is now being explained away as being purely diagenetic, but it really fails to recognize the fact that, there is a mass extinction then. So I think that it feels, just to play devil's advocate, it feels like the pendulum has possibly swung too far. I'm
playing devil's advocate too, because I rely on making a lot of these measurements. And so it's sort of, in some ways, I just like to throw it out there as a question. And I don't really want to throw the baby out with the bathwater here. But then the question becomes is the Hernantian, a carbon isotope excursion because there's a global perturbation to the carbon cycle that's interpreted in terms of fractional organic carbon burial, which is what I posited? Or is it that, there's major sea level change, which changes depositional environments such that the carbon isotopic composition of what's preserved is different? And so there's two ways around that sort of a question. And, I read and I review too many papers where every change in the carbon isotopic composition is plotted right next to a change in fractional organic carbon burial. And I want us to start questioning that, not only from the point of view of diagenesis, which is, I think exceptionally important, but also from the point of view of the other 2 points I made, which is that I don't know that we can guarantee that the carbon isotopic composition of volcanic material or rock material has stayed the same over time. And, and the fact that organic carbon has this range and can be preserved differently in different environments. And I guess what I think, sorry.
Just to let you know, there's several people with their hands up who want to get.
Yeah, no, absolutely. We were just playing for time there. Kathy.
Volker's got his hand up.
Kathy
Sorry.
and Volker.
Kathy was here first.
I'll let Volker. Sorry, I was going to say I'll let Volker go first because I suspect he's going to follow up on what Sasha was saying.
Okay, so but I'd like to come in because it's pitching a little bit what Megan said in her presentation today as well, right? That in a we talk in Bahamas, that the carbon isotope changes are diagenetic, yeah. And this is a long-standing debate. I think she makes a very good point. And of course, if you have a global sea level change, then that can be at the same time. But if you have, I think the onus is a little bit on making sure you can correlate it over wide distances to many different places, different depositional environments, etc. Then I think you can argue the case, especially if you can connect it to other environmental factors that were changing.
Yeah, so I completely agree with you. And unfortunately, we've got a machine being installed this week, so I've been in and out and not able to attend all of the meeting for the last 2 days. And I actually, when I was thinking about this question, I was thinking about a Precambrian world. I wasn't as much thinking about the Phanerozoic carbon isotope record, to be honest. And I was thinking about the circular argument or the circular thing that you get into, where I find a carbon isotope excursion here and I find a carbon isotope excursion there, and neither of them are particularly well dated, and I do not have biostratigraphy. And so therefore I line these two carbon isotope excursions up and assume that they are more or less synchronous, which is done throughout the Precambrian rock record, where you don't necessarily have the age constraints that we have from the beginning of the Phanerozoic. And so that's the world. I mean, that, and when you think about like +5 per mil carbon isotopes in all carbonate minerals for 300 million years in the Neoproterozoic, what's driving that? I wasn't thinking about mass extinctions as much when I posited these questions. I'm thinking about interpreting some of the deeper time records in terms of changes in fractional organic carbon burial, and where you don't necessarily have the ability, except for the fact that I find these two carbon isotope excursions, so I might as well put them up synchronous with one another rather than actually considering whether they actually are temporally synchronous.
Of course, if sea level change, eustatic sea level change is our mechanism, then we've got something there to as a framework that would suit all these needs. It would be a framework to nest all these processes synchronously. Sorry, Kathy, go ahead.
Well, yeah, sorry, I was just going to follow on from that, actually. I was going to say something different, but yeah, I think that you then get into the issue of what is actually a global sea level change and what isn't as well. So the problem doesn't really go away, because what might be interpreted as being global could well just be a local effect of tectonism or whatever, but it creates other problems. I think what I was going to say was more around the dolomite, and I think when it comes to dolomite, then it's really quite dangerous to start looking at global trends without any petrography, because I just put in the chat, there's very little primary dolomite in the Phanerozoic. Most of it might have been some seeds or some very high magnesium calcite formed that would give us some indication of local or global conditions, but most dolomite is going to be forming diagenetically and will probably have grown over several periods of recrystallization. So trying to tie in global trends without looking at the petrographic evidence for that is really quite dangerous. And I think, you know, that there's been these curves modeled before in terms of dolomite abundance over time, but when you look at them, a lot of that data is quite regional or quite basal. So I think absolutely we need to be looking at these in a lot of detail and looking very carefully at where samples have been drilled and what sampling mechanisms are.
Thank you. Can we have a comment from Hillary's next to make a comment, and then I think it was Axel and then Jim.
Yeah, my comment was just to speak to Sasha's point about the potential local effects, and also I would say in carbonates, obviously we always have to worry about diagenetic effects, and I find that it can be really helpful to pair any carbonate platform study with also looking at shales and looking at the signature in shales, because obviously they're not as diagenetically susceptible. I don't love looking at shales, obviously, but I prefer carbonates, but it can just be really helpful to get that sort of, you know, you can do organic carbon, and you can even evaluate if they're a more lime mud type shale, you can evaluate carbonate in there, and that can be really helpful. I've done this in a couple of locations in the Western Canada Sedimentary Basin that's, as we heard earlier, has been really affected by later diagenesis, and you see a totally different signature in the shales than in a lot of the carbonates. So that was just my comment on that. I think it can be a helpful tool.
Yeah, I think it's an excellent point. I guess the thing I always worried about shales and lime muds are cements that are from isotopically evolved fluids. So this sort of perennial problem of sort of cements that are growing from pore fluids that are not that of seawater. And obviously, if you could systematically evaluate all rocks that were deposited in all environments at any one point in time, then it becomes a lot easier to understand what is meant by a global sink, and a global source. But in the absence of that, I agree that, looking at multiple proxies from the similar stratigraphic intervals really helps bolster our understanding of what aspects could be attributed to diagenesis and which aspects might be referring. And someone put in the chat this idea of measuring the whole rock as well as a fossil, which again, I wasn't necessarily thinking about, Phanerozoic questions. I was thinking about sort of using carbon isotopes over the course of Earth history, which is often done in micrites and is often done in sort of in limestone rock facies and whatnot, and just whether we should start questioning those assumptions.
Mm-hmm. So I think Jim has his hand up, and then Chihang.
Yeah, thanks. Just going back to Kathy's point about dolomite, the apparent correspondence of dolomite abundance with mass extinctions, it just sort of crosses my mind that these intervals are going to be intervals that have been studied intensively precisely because they are mass extinctions. So how reliable is that curve? And when we talked yesterday about uncertainties, I think that's quite an old curve, isn't it, for dolomite abundance? Do we actually put a lot of weight on it still?
Yes, I agree. There's a lot of devil in the detail here. It's actually, I thought that curve was a newly formed curve from this year. It's a geology paper.
Okay.
But exactly how they measured dolomite abundance was perhaps not the most robust way. So I totally agree, of course, that there's a lot of devil in the detail here. Yeah, absolutely. Having said that, there does seem to be I don't know whether, Nick, whether you want to comment on this relationship between dolomite and anoxia. Is it a red herring? Does it exist?
I mean, I'll just say that, yeah, so the relationship between dolomite and mass extinctions, I mean, yeah, that I think Jim's got an excellent point. I mean, if you think back to, to the Given and Wilkinson papers, and they looked at dolomite abundance versus sea level, it looks an awful lot like that curve. I think it's difficult to disentangle causality here, and I think Kathy brings up a good point that you've got to look closely at the petrography to really know whether this is syndepositional or early diagenetic and not just recrystallized. the links to redox, I mean, some studies have made this claim. Again, there are modern dolomite forming environments in oxic fluids. So to me, that's not entirely satisfactory. But I'll leave it there.
Yihang and then Peter Swart.
Hi, I was wondering, since Nick mentioned this, is it possible, do you think dissolved silica could be one of the magic ingredient for dolomite formation, like at least for primary dolomite formation, especially in the earlier history?
I think it's difficult to know. I mean, it's an attractive candidate. Silica was certainly, well, at least the thinking is that silica was enriched in Precambrian seawater, although we don't actually have a lot of hard constraints on that, aside from the ubiquity of early diagenetic chert. I know there are some cave environments or dolomite forms where there's essentially no silica. So, again, I hate to sort of harp on those issues, but I think if you're talking about the issue of dolomite formation, you've got to include, the whole range of different environments that are capable of forming ordered dolomite as well.
Thanks.
Peter.
Hi, I just wanted to chime in on Rachel's comment about the fact that we're turning away, and starting interpreting things which were previously interpreted as being real, as carbonate excursions. And all I have to say, it's about time, because, I've been actually appalled at the misuse of carbon isotopes for about maybe 30 years, and it went from a stage where we were very cautious. I'm talking about the 1950s, even in the 60s, we already knew that these things were heavily diagenetically altered, to a point where everything was interpreted as being original and every carbon isotope was beautiful and this, that, and the other. And, when I started trying to cast some, I don't say doubt, but, some caution on this, I was treated like a complete heretic. And, and I'm glad to see that at least some of this is filtering through, that we're recognizing that there are other things that are controlling the carbon isotope record, and just because we see a signal in all over the world doesn't mean that it's, reflects the global carbon cycle. And I'm not saying that, there are not cases where it does, but certainly there are a lot of cases where just because it's global, and as Megan showed this morning, and this was basically a follow-up from the paper that Martin and I did a few years ago, that, it is possible to have a global diagenetic signal. And I think to follow up, I think it was on Fiona's question to Megan this morning, there are certainly, we could get a lot more sophisticated on how this sea level change is manifests this signal during different parts of the Earth's history. And just to give you an example, in the Bahamas, we've had, it's well affected by the last 2 million years of glacier eustacy. But I don't know if you realize that in the last million years, the Bahamas was actually only under seawater about 95%, 5% of the time. So 95% of the last million years, it's been high and dry and been altered by meteoric diagenesis. Now, if you compare that to the atoll, it's quite different. There, because it's a keep-up system, and the thing is, it's accreting like mad, and this atoll is subsiding. The sea level has a different type of an effect, and you can imagine that in the Cretaceous or some greenhouse period, this will lead to quite different types of diagenetic signals. So it's actually quite a worthy thing to look at. Just to try to extend this analogy, not only go back to periods, other places other than just Eniwetok and the Bahamas. I always find it's quite interesting that there are less, good cores to the Pleistocene, meteoric than they are through, less studies in the Pleistocene than they are, for example, in the Neoproterozoic in terms of this kind of signal. You know, we're looking around for looking at global signals of Pleistocene sea level changes in shallow water carbonates. There are not that many nice good cores. And of course, there's the Bahamas, there's Inuitak, there are a few other ones, but not. You know, it's difficult to show a global signal by looking at these kind of things. So anyway, that's my rant, my two cents on this.
Thanks, Peter. I know we're running out of time slightly here. I think Fiona wants to make a point, and then maybe Pete, you could synthesize your very lengthy chat into a question. So Fiona, then Pete.
My point was very quick to make in that, and it was kind of in response to something Nick said, in that I'm sure there are environments where dolomites form in the modern which lack some key magic ingredient, but is it a mistake looking for one key magic ingredient, or are different factors likely to be important in different environments? So maybe rather than throwing individual ideas in or out, saying we either pass this barrier, this criteria, or we don't. Does it apply everywhere we get dolomite? No, so it can't be important. I think there may be different factors that are important in different conditions.
Absolutely, Fiona. Just to respond to that, I don't think we should be looking for magic ingredients at all. I think that's not a fruitful way to address the problem.
Okay, so can I just say quickly something about the Dolomites? I mean, we know we have a lot of Dolomites in the subsurface of the Bahamas and the atolls and Southeast Asia, which is very, very young. And mass balance calculations, I think there's no way around, and Fiona has done this before, and we have done this. Just basically requires that seawaters has to circulate in massive quantities through carbonates to cause massive amount of dolomitization. And I think recrystallization later on and overprinting, as we have seen in the talks earlier, is possible for sure, you know, because a lot of the modern or more modern dolomites are not perfect dolomites. But if they are dolomites at all, if I understood the discussion correctly, but you know, it doesn't. It's no way around that the dolomite, you know, in most cases must have a marine origin before it is being overprinted. You know, and if you look at, you know, massive amounts of dolomites in carbonate platforms, and we shouldn't forget.
Pete, did you want to chime in with your question or your comment?
So this is not my area at all, but there's definitely some parallels, and I think I can summarize it and say we shouldn't really expect simple answers in complex systems. That's just not going to happen. And actually, the sooner we embrace that simple fact, I think the more progress we'll make. Maybe I don't mean to say that everybody's being ridiculously simplistic, because I think this conversation is going in the direction of more complexity, isn't it? Multiple controls.
Welcome to the world of carbonates.
Well, yeah, I mean, we all say it, don't we, in lots of ways. But, you know, interestingly, I'm not sure that we often really truly embrace it in terms of what we then go and do and try and, you know, interpret, because our interpretations often aren't very complicated.
Well, we're simple people. We've got to start with simple things and then make them more complex. So it's easier to start with things simple and make it more complex.
Well, yeah, that's interesting for you. See, I'm not sure that it is, because I think what happens often is you just get locked in those simple models, and then you just get stuck, and you kind of expect that to be the truth. And it, you know, you all seem to be saying that, you know, in various different ways that it's not. I mean, in my area, it certainly isn't, right? But I'm just go nuts with people appearing to assume that it really is that simple, and they can therefore, you know, ignore lots of complexities.
I think that's right. But I think the community has become sort of anchored. You know, it's almost like an elicitation exercise where you've got anchoring of attitudes, and maybe there's actually there is very powerful common ground to be had. Georgina, and then Hilary, and then I think we probably have to stop.
Yes, thank you. I wanted to follow up on what Volker mentioned, since I'm very interested in dolomite recrystallization. So, basically the question of how recrystallization actually affects the carbon isotopes, which I'm not entirely sure that we fully understand that. And also to what extent these dolomites are actually recrystallized, because again, I think that's kind of a fundamental problem that often it's not even considered that these dolomites might actually be recrystallized, and the value that are measured are not actually representative of, not even the dolomite, original dolomite, let alone the seawater. So yeah, that's basically my comment / question of, people who are more familiar with isotope fractionation processes during recrystallization.
Okay, Hilary, did you just want to say something very briefly? And then I think.
Oh yeah, mine was just going to be another. It kind of came up when Rachel mentioned the Hernentian. Like I think, and I thought of this yesterday too when we were talking about some of the automated deep neural network sort of classification of carbonates. I worry about some of that from the perspective of losing touch with the signals that the organisms are sending us. So like the importance of petrography and detailed core logging and section logging for looking at the hints that we get from biology. Because I think when we miss things like, even just the direction a shell is oriented, or what's happened to that shell since it was deposited, was it eroded or not bioeroded? Did that tell us anything? I think that these are signals that we could miss with some of these automated things. And then that can, when we're trying to interpret a carbon isotope curve and we see something that says, oh, there's a huge problem here, there's probably a lack of oxygen. And then you go and look at a core that's in that exact interval and it's completely bioturbated. Well, it couldn't have been anoxic if it was completely bioturbated. It might have been suboxic, it might have been disoxic, but I think that these are signals we can't ignore. So just, I guess, a cautionary tale from all of my old supervisors and what I tell my students too.
Okay, I'd like to thank everybody that contributed to the discussion. We can